So we're still looking at exercise 1, now the last part of the exercise. We're asked to consider a mixed Poisson process N, in the sense that this thing here is a standard homogeneous Poisson process evaluated in theta t, where theta is a random variable. Then they say, what is the point probabilities for N if we assume that theta is gamma distributed with these parameters? And they actually give us what the density should be for theta. So the density, they tell us, is beta to the gamma divided by the gamma function evaluated in gamma, multiplied by x to the gamma minus 1, multiplied by e to the minus beta x. And here we assume that x has to be positive. It's always nice to get the gamma probability density because you never really know which parameterization people are using. So this is the density we will be working with. And apart from that, we have a very nice result from 1c that we have just done, namely that the point probabilities of a mixed Poisson process are given as t to the k divided by k factorial multiplied by the mean value of, was it theta to the k multiplied by e to the minus theta t. So since we now know the distribution of theta, we can calculate the point probabilities of n using this formula. So let's get started. I want the probability that n of t is equal to k. So I try to calculate this thing here. I have t to the k divided by k factorial. Nothing interesting so far. But then I want to calculate the mean value of something where the random variable in question has gamma distribution. So I want to consider which variable should I use here? Well, let's just use x, because that's also what they use in the PDF solution, and then it's easier for you guys to follow. Okay, so this is x to the k multiplied by e to the minus xt, and the gamma density goes from 0 to infinity, and I plug in the expression as well, beta to the gamma function evaluated in gamma, x to the gamma minus 1, e to the minus beta x dx. Okay, so one thing that we should recall from each time we worked with gamma densities is that we often use that trick where we try to arrange things so that whatever is inside the integral is again a gamma distribution density. And then we can just say, oh, this thing integrates to 1, we're finished, and so on. So let's just try to group everything inside here so it looks more or less like something that comes from a gamma distribution density. So what I have inside, I can just take the beta to the gamma and the gamma of gamma out here. So what I have in here, if I group the x's, I have x to the k plus gamma minus 1. And I group the exponents, I have e to the minus t plus beta x, the x, right? And the thing that I can try to do now is say, well, in a gamma distribution density, I need to normalize whatever is inside by using these two parameters here and constructing this fraction. So I can normalize whatever is inside here by considering, well, let's see, t plus beta to the k plus gamma, so this parameter, divided by the gamma function evaluated in this parameter, which is k plus gamma, right? And now I've multiplied with a normalizing factor outside of all of this, and essentially I'll use that trick where I just multiply by 1, in the sense that I multiply by fraction here, and then I just multiply by the inverse of that fraction. So basically I've just multiplied by 1. And this is very nice because then what we can do is we can recognize something as a gamma distribution density, and the thing we recognize is this entire bubble here. This integrates to 1. And so what we're left with is t to the k divided by k factorial, and then we have beta to the gamma, and what else do we have? We have gamma of k plus gamma divided by gamma of gamma, and then we have somewhere t plus beta. Sorry, I have to divide by that. So 1 divided by t plus beta to the k plus gamma. What can we do from there? Well, we can kind of consider what we can do with this thing here, right? So I can group the t to the k together with the t plus beta to the k down here. So this is all to the k. And then I have beta to the gamma, and over here I have t plus beta to the gamma. So I can just take out the gammas outside the parentheses, where I take the entire gamma power of this. And then what I have left is gamma of k plus gamma divided by gamma of gamma multiplied by k factorial. Now, what can I say? Can I say anything in particular? Well, we can use the fact that the gamma distribution is sort of used as a kind of generalized factorial, in the sense that whenever I have an integer n, then gamma of n is equal to the factorial of n minus 1. Now we will kind of generalize that in the sense that we do not require gamma to be integer here. We'll just write it up with this kind of factorial notation. So using that factorial notation, I get equal to t divided by t plus beta to the k, and then beta divided by t plus beta to the gamma, multiplied by k plus gamma minus 1 factorial, divided by n divided by gamma minus 1 factorial multiplied by k factorial. So this is like kind of the generalized binomial coefficient, which we write as k plus gamma minus 1 choose k. And then I have t over t plus beta to the k, and I have beta over t plus beta to the gamma. And actually now we are done, because this is exactly also the individual probabilities that you see in the negative binomial distribution. We can kind of, we can call this t over t plus beta, we can call it p, and then we can call this one 1 minus p, because you can see that they do relate to each other that way. And so the answer to the question, why do we call the process a negative binomial process? Well, it's because that the claim number at time t, n of t, is indeed negatively binomially distributed in a certain sense. So this is a nice result, and especially when gamma is an integer, we will get, oh, not an integer, when it is a positive integer, we will get a result that is that we will get a negative binomial distribution that resembles the one that we know. So that was exercise 1